There's been a lot of tsunamis in Japan. Japan's location on the Ring of Fire has made it one of the most seismically active countries in the world. Throughout history, tsunamis devastated its coasts and caused disasters. But tsunamis are hard to predict, even using modern technology. On March 11, 2011, a 9.1 magnitude earthquake struck 45 miles off the coast of the Ashika Peninsula. It caused a massive tidal wave with a peak height of 132.8 feet, which compromised the Fukushima Daiichi nuclear power plant's safety systems. This triggered a nuclear disaster on a scale not seen since Chernobyl. Hundreds of thousands of lives were uprooted in the wake of this tragic collision between Mother Nature and technology. And yet, the disaster at Fukushima Daiichi was but one of many tragedies from that day. So how is Japan working to prevent the next disaster? Japan has been formally studying tsunamis and developing countermeasures since the 1896 Sanriku earthquake, which produced waves peaking at a then-record 125.9 feet high. In the advent of the 2011 tsunami, Japan's Reconstruction Design Council, an advisory panel to then-Prime Minister Naoto Kan, has proposed implementing 2 classes of tsunami protection for varying levels of severity. This differs from the internationally used Tsunami Intensity Scale, which grades tsunamis on a 12-point scale. For L1 grade tsunamis, or tsunami events that occur every 10 to 100 years, physical protection has been implemented in at-risk areas. Structures such as seawalls, breakwaters, dikes, and floodgates line the coasts of towns that may be affected by this class of tsunami. However, protections for L2 grade tsunamis, or tsunami events that occur every several hundred to 1,000 years, have mostly been soft measures proposed by the government. For settlements at risk of being completely annihilated by a tsunami of this magnitude, the RDC has recommended land zoning and evacuation plans, bolstered by improved tsunami detection technology. Aside from this, relocating communities to higher land has proven to be the most effective measure to prevent death during a tsunami, and has been in practice since the Great Kanto earthquake's resulting tsunami in 1923. Japan is also using cutting-edge computing technology to help identify at-risk areas with even greater accuracy. The supercomputer Fugaku. This mammoth of a computer is powered by 158,976 individual CPUs, each running 48 high-speed multi-threaded cores. It is currently the fastest supercomputer in the world. By analyzing data from past tsunami events, the supercomputer is able to simulate 20,000 different potential post-tsunami scenarios. Fugaku is able to simulate flooding scenarios in various regions throughout Japan by combining AI and a deep learning algorithm. This enables the government to plan and build protective structures for coastal regions more effectively. In use throughout Japan since the 1930s, seawalls were originally introduced as a way to block incoming tsunamis from making landfall. While they do offer protection to coastal areas in the event of storms and larger tidal waves, the destruction caused by the 2011 tsunami has led some to doubt their efficacy. Furthermore, their growing presence has caused a great socioeconomic and environmental strain on surrounding areas. Despite these concerns, the Japanese government decided to double down on the usage of seawalls. Following the 2011 tsunami, it allocated upwards of $17 billion for the construction of new seawalls to replace those destroyed. Dubbed the Great Wall of Japan, this construction project spans over 245 miles in length at an average height of 42 feet. Japanese engineers have also been working on new designs to compensate for the drawbacks usually associated with seawalls. They propose a new type of seawall, the recurved seawall. The main difference between this and a regular seawall is its concave surface facing the sea. In small-scale tests, Engineers have found that this design significantly decreases the wave overtopping rate, which is the amount of water displaced by a wave as it passes a seawall. However, during these tests, engineers have also found a potential weakness in the design. It also increases the force generated by the breaking waves. To address this weakness, engineers have proposed these seawalls to be constructed using reinforced steel and high-grade concrete, thus improving their structural rigidity. A seawall has already been erected with this design. The flaring-shaped seawall, built along the Osaka port in Kurahashi-cho. Engineers have also been working on new ways to construct traditionally designed seawalls. The main problem with the construction of old seawalls is the main material used, concrete. Due to its brittleness, concrete tends to not only break, but also increases the force of a wave, worsening its potential effects when it meets land. To remedy this, Japanese engineers have adopted a different design philosophy for their seawalls. Newer seawalls are laced with steel hoops, which encourage movement during a tsunami event, provide ductility to these structures, and prevent large chunks of it from becoming deadly debris in the event of a break. Plans for upgrading the now-defunct Hamaoka nuclear power station offer us a glimpse of how future buildings along Japan's coastline may be constructed. These plans feature a 59-foot-high embankment spanning 0.93 miles along the coast, a waterproof building for a backup pump, as well as reinforcement for its already formidable barrier wall. Proposed to be 33 feet higher than even the resulting waves from 3 simultaneous 8.5 magnitude earthquakes, this barrier features a nearly all-steel construction. The Hamaoka nuclear power station also comes equipped with sand hills up to 49 feet high. Despite engineers claiming the safety of the facility, Japan's then Prime Minister Naoto Kan called for its operation to cease just months after the 2011 tsunami. Potential solutions for tsunami-proofing Japan's buildings have also come from external sources. Cambridge professor Dr. Gopal Matabushi has recommended a different design philosophy for building construction moving forward. Matabushi advises that buildings should be designed and built with the intention of allowing water from tsunamis or floods to flow through easier. One way of achieving this would be by featuring an open design on the first floor by installing larger doorways and windows. Some buildings could even feature designs with the entire ground floor open by raising the structure above ground on stilt-like foundations. The end goal of building buildings in this way would be to protect foundations and make reconstruction efforts easier. Given Japan's close relationship with the sea and its reliance on seafood, finding ways to mitigate the damage caused by the next big one is extremely critical. This sense of urgency is ingrained in its citizens as soon as they enter elementary school, and it's part of their deep sense of responsibility to themselves and others.